6.2, differential equations, growth and decay. In many applications of integration, the rate of change of a variable y is proportional to the value of y. In other words, y prime or dy dt, the rate of change of a variable y is proportional to y. So when you see the rate of change of a variable is proportional to the variable, this is your setup. And when this is your setup, you have a general solution, which is a growth or decay model, and it becomes y equals ce to the kt, where y is a differentiable function of t, y is positive, c is the initial value of y, and k is the constant of proportionality. So exponential growth will occur when k is positive, and exponential decay will occur when k is negative. So let us look at a proof of this theorem, how this relationship becomes this one. So we will start with y prime equals k times y. That's our given equation. Now I'm going to write that we have dy dt, which is y prime, equals k times y. And I can do something called separate the variables, which means to bring the y terms on the same side and the non-y terms on the other side. So I have dy over y equals k times dt, and that is what we're going to integrate. Now there is another way to get there. Thinking about this as y prime over y equals k, and knowing that y prime is dy dt, what I have here is the integral of y prime over y with respect to time equals the integral of k with respect to time. And so y prime dy over dt over y times dt, the dt's cancel, I get 1 over y dy. That's what's going on. I think this is a more clear way to get there, but either way, I get here. And now we're going to anti-differentiate each side. Well, we know that this becomes ln of y, and I don't need the bars here because I have stipulated that y is positive. Equals, with respect to t, k times t plus some constant c, and I'm going to call that c1. Okay? And now, remember our old phrase, log is exponent. Log is exponent. This is my exponent on e, and it equals y. Y equals e to the kt plus c1. Now, let's remember a little algebra. We know that e to the a plus b is e to the a times e to the b. So e to the kt plus c1 is e to the kt times e to the c1. What is e to the c1? That's just some other constant. We will let c be a collapsed constant of e to some power c1. We don't really know what our c1 is, so we don't know what e to the c1 is, so we'll just call that our big unknown constant, c. And this is how we get from here to here. It uses a technique called separating the variables, which we'll look at more in the next section. The rate of change of y is proportional to y. When t equals 0, y is 4. When t equals 5, y is 1/2. By the way, notice my y values are going down, so this is going to be a decay problem. What is the value of y when t is 3? Well, we know one thing. It's got to be between 4 and 1/2, because when t is 0, y is 4, and when t is 5, y is 1/2. So when t is 3, we have to have a value for y that clearly is going to be between these two values. And so we know that as a checkpoint. Now, we are told the rate of change of y is proportional to y. That always means this, which always means this. We need c and k, so we're going to need to do the algebra to find these using this as our basic equation. When t is 0, y is 4. We get this, and we get that c is 4. So now we have our c, and our equation becomes y equals 4e to the kt. Now we need our other point to find k, our other point being when t is 5, y is 1/2, and we're going to use our calculator to get the answer. Now, for 5 1/2, again, 1/2 equals 4 times e to the 5k. And let's remember what we learned in algebra. Let's isolate the exponential part before we take the logs of both sides. So I'm going to divide by 4, gives me 1/8. And now I've isolated this. We will take the log of both sides of this equation, which gives me natural log of 1/8 equals natural log of e to the 5k gives me 5k. We're solving for k, so let's divide by 5. The cleaner way to write this is 1/5 times this. This is your exact value for k, which isn't really helpful for us. We need to have something we really understand. So we're going to use this and use the calculator with one calculation to get this answer. Now, k is really approximately negative 0.415888 and some other numbers, right? We want to store this. We're not storing that. We're storing the k value that is on the calculator because we're probably going to use it in other parts of the problem. When we write it out, we will write this number as our k in the equation, but we're going to use our stored value. So here is our equation. Y is equal to approximately 4e to the negative 0.416t. So using our approximated equation, when t is 3, we can substitute in, and we get y is approximately 1.148 if we truncate, or 1.149 if we round. Either answer is acceptable. So what happens when we do not give a condition when t is 0? Well, we do what we learned how to do in algebra. Find the model for the function which passes through the points 2, 2, and 4, 6. Well, this is our coordinate pair ty. Our equation is y equals ce to the kt. So when t is 2, y is 2. When t is 2, y is 2. And when t is 4, y is 6. So one way I can do this problem is to take these equations and divide them. So I'm going to take this equation, divide by that equation, which gives me this, and the c's can cancel. And I get 3 equals e to the 2k. Like the last problem that we did, we now are ready to take the log of both sides and solve for k. Another way to have done this is by substitution. Rewrite one of these equations to solve for c. So taking this and solving for c. But this brings up a really good thing for us to remember. C is 2 over e to the 2k, which means c is 2e to the negative 2k. Okay? And so we're going to make that substitution into this equation. There's my c. What do I do when I have the same base and I have exponents? We add the exponents. Negative 2k plus 4k is 2k. So we get, dividing by 2, 3 equals e to the 2k. So I get the same equation, which means I should get the same answer. Now we're going to store that value for k. And to store that value for k, I can now find c, and I can use either one of these equations using our stored value for k. And I'm now finally able to write the equation for my model. Y is 2/3 e to the 0.549 t. And there's my equation for the model. I will leave it to you to be sure to look at examples 3 through 5 that happen on page 415 to 416 for other applications. Newton's law of cooling is another growth or decay model. What it states is that the rate of cooling of an object is proportional to the temperature difference between the object and its surroundings, provided that the difference is not too large. So the rate of cooling dt, capital T, the change in temperature with respect to time, is equal to K times the difference in the temperature of the object and its surroundings. T sub 0 is the room temperature. Here's an example. A cup of water with a temperature of 95 degrees Celsius is placed in a room with a constant temperature of 21 degrees Celsius. How many minutes will it take for the water to reach the temperature of 51 degrees Celsius if it cools to 85 degrees Celsius in 1 minute? Notice that our temperature is going to be bounded by 51 and 95, okay, because we want to find how long it takes to reach 51 degrees. So my general equation, dt dt, is K times T minus the temperature of the room, 21. And separating these variables, getting the t's together, is going to bring this binomial here. You should recognize what's going on here. U prime over u equals K times dt. Anti-differentiating both sides gives us the natural log of absolute value of t minus 21 equals K times t plus some constant c. Now, we know that this side, log, is exponent. So t minus 21 is going to equal e to the kt plus c1. And we know that e to the kt plus c1 is going to resolve itself down to c e to the kt. And solving this for t would mean to move the 21 over. Now we have at least our model. And so we're going to find the particular situation for this problem. We have at time equals 0, our cup of water was 95 degrees. So our temperature difference is 95 minus 21, which is 74. And so I have 95 minus 21 equals C e to the t is 0 is going to give us this. It gives us C to be 74. So there we have that. Now we're going to find K using the other information, 1 minute to 85 degrees, substituting 1 for T, 85 for my capital T for temperature, gives us, again, you want to get everything into right here, and that's 64 over 74, which does reduce to 32 over 37. And now we're solving for K, so we have to take the log of both sides. So we get K to be negative 0.145 and a bunch of other decimals, so we're going to store that. And now we are ready to finish the problem. Now we have our model for this situation. For now, the temperature, that is 51. We want to learn how long it takes to get there, and it takes about 6.227 minutes, so about 6 1/4 minutes about. And on page 417, you'll see an example using Newton's law of cooling. So your 6.2 TPs are 5, 11, 21, 25. See you next time.